The first characteristic of a system is that it exists in an environment. And that's pretty obvious because everything exists in some sort of environment. But why this is interesting is that we actually need to think about the boundaries of the systems that we're dealing with. And when we talk about systems, we need to think about how do we delimit them from the other systems and how do we delimit them from our environment? One of the systems that we are dealing with on every day is our own body. I mean, our body is a unit that we can quite easily delimit from the environment because it is separated by the environment with skin. But within our body, we have different systems happening as well. We have the circulation system, and every single cell is its own system. So if you think about, let's say, Amazon is as a whole a system that consists of information platforms that have some sort of, it's a website, right? It has some sort of logistics tied in, a logistics system. It has payment. It has an internal process flow that would actually generate maybe some offers or some sort of marketing, whatever it is. But then the question becomes, where does Amazon as a system start and where does it end? If they work with Visa for the payments, that they are interfacing now with Visa at this point, and they have their own payment system, but they are actually dependent on Visa as a system operator. So there we have a first interface and we have a first boundary that needs to be defined, who is responsible for which. We have inputs and we have outputs. So input could be, if you go back to Amazon, it could be the input that I'm looking for a specific item. I want book XYZ. So I'm giving them the information, that is an input. I'm giving them money, that's another input. And then I have an output, which means that I have the book in my postbox in the end. Amazon as a system is for me a black box. I don't care, to be honest, what happens at Amazon. So you have systems that you are not actually privy to the information of what is happening inside them, and it's not very relevant for you. So we often deal with black box systems, and in a lot of cases, when we actually develop the system, then obviously we need to understand what happens in them. I've already talked about the interface with other systems, and it communicates with them a lot, so I don't have to go into that too much at this point anymore. But just to remember that we also deal with hardware interfaces. We also deal with interfaces that are outside the realm of computing, where we deal with other businesses, we deal with regulations, we deal with governments, and all that matters when you talk about how you're actually developing systems and designing them. There may be subsystems. At Amazon, you have a subsystem being their payment system is, for example, a subsystem of the whole. And these can then have further subsystems yet again. And there should be control mechanisms generally. You need to have some sort of mechanism that tells you whether the system is still healthy, right? Whether it's still working. And generally we have feedback and we have feed-forward loops in the control. Usually when we think about feedback, that is the most common way of improving our system or any process really. We look at how did we do something and did it actually achieve what we tried to do. Feed forward would be when you actually look at the whole thing from the beginning of the process, right? And you say, what can we anticipate about what we need in our process? So one thing could be Amazon saying, well, we've suddenly had a lot of pre-orders for the latest Terry Pratchett. You know, then they will have to adopt that. They will say, wow, that's a lot more than we actually anticipated. So that's a feed-forward system where you say, we need to actually adapt to that. We need to have more people, you know, shipping out Terry Pratchett's than we actually originally thought. And it has emergent properties. And that means simply that a system is more than just some of its parts. There are some criteria that make systems good systems. The first is it useful and is it usable? Usable being we are looking at, can people use it the way it is designed? Is it actually functional? That's the very first question, right? If I click on button X, does it actually do what it's supposed to do? But then you also have usable being all sorts of additional needs, international, but we also have questions of, can people with special needs use the system, for example, right? Is it usable for the people that it was designed for? Is it useful? Can it actually improve whatever it is we're trying to do? Then it has to be reliable. That's the second criterion that we want. So how much downtime do we have? We can say about bugs, so when it actually does not work the way it is expected to work, we can look at it from a perspective of how many users does it actually affect and to what extent does it affect them. So does it actually mean they can't use the system at all? Does it mean they can use the system only partially? Does it mean that it's more laborious to use it, or is it just a beauty issue? Is it flexible? So the first thing is, can bugs be fixed? That doesn't go without saying. Developing systems can also mean that you're actually, if you don't set them up properly from the beginning, if you don't plan the architecture correctly at the beginning, you might run actually into problems where even if it's a low risk situation, fixing bugs would be such a big task because you have to do so many changes to the code that you originally had that you might actually end up with an entirely different system than you originally had set out, or that you might that it might not be beneficial financially, or that you will actually not be able to get to the point where the system is still usable in the end. But also, can it adapt to changed user needs? It's all well and good if I say, well, I'm going to be very reactive to your needs, right? Tell me what you need, and I'm going to make it happen, right? I can be very willing to do that. But if my code is set up, my system is planned in a way where it doesn't allow me to actually do that, then then that's not a very useful system for that particular situation. Affordable, of course, the cost of development, but also the cost of maintenance. So if the system goes down, if the system has bugs, what does it cost to actually deal with that? But you also need to see, I mean, affordability is of course always about cost and benefits, right? I mean, some software products are very expensive. SAP produces software that is very, very useful to a lot of people, right? And in a business setting, very, very good. But of course, it's not something that I, as an individual, would ever buy for myself, right? Because it is expensive, and it's just not would never give me the benefit that I need there, right? And then the availability. So of course, does it exist? But also, does it actually work on whatever system I'm trying to operate it on? If I'm a great fan of Apple computers, but I can't actually run whatever I'm trying to run on an Apple computer, then that is not a very good system for me in that situation.